The dot product was an inner product. There are exterior products and entire sets of things called exterior algebras. They're less useful at this point than this version, which is specific to R3. It only works in 3 dimensions. Exterior products can be generalized to be lots of other places, but cross product or the vector product. Vector as opposed to scalars. So we're going to output a vector this time. I'm going to multiply these 2 vectors, and I'm going to come up with a new vector. Now, there's a formula. I'm going to write it down. You shouldn't, because this formula sucks. A cross B has as its 3 components A2B3 minus A3B2, then A3B1 minus A1B3, and then A1B2 minus A2B1. This is disgusting. And the reason I don't want you to write this formula down is because there's a better way to remember it. But that method requires me to take a short diversion in a piece of linear algebra called a determinant. A determinant is a way of taking an array of numbers and getting a single number out of it. It's an inductive procedure, a recursive procedure. So I start with a square array, 2 rows, 2 columns. And the goal is to pick 1 from each row and 1 from each column. And look at the ways you can do this. Well, it turns out in this, there are only 2 ways to do that. If I pick 1 from each column, I can do A1, B2, and then I can do A2, B1. And since we think of A as coming before B, I think of 1 as coming before 2, these are reversed from the right way. These are in the right way, right? A comes before B and 1 comes before 2. Here we've got a reversal. So I'm going to subtract. Visually, I take these 2 and I take these 2. And I add the product that went down and I subtract the product that went up. Top left times bottom right minus bottom left times top right. That's a single number called the determinant of this 2 by 2. To do a 3 by 3 array, I really need to do 3 2 by 2s. And this is a method of finding the right sub-pieces in here. Technically, this is called an expansion by cofactors and minors. And if you've taken linear algebra, you know what that means. And if you haven't, I promise I'll explain it there. And if you're not going to take that, just trust me on this, it works. But I pick a row or a column, and for this course, I'm going to use the top row 99.9% of the time. So I say, let's start in the top left corner. Get rid of that row and that column, and you will be left with a 2 by 2 submatrix, won't you? That's called the minor. So what I'm going to do is I'm going to take A times that little 2 by 2. Now I'm going to go across the top row. So you'll notice what I did is I got rid of that, and there's my little submatrix, the minor. Now I'm going to do that here with B. Well, this one is added. When I do B, what's my subminor? submatrix, the minor. And that one is subtracted. So I start with a plus, I move over, I get a minus. I'm going to move over again. It's going to switch back. What's that minor? Perfect. And then I'll get a 2 by 2 and a 2 by 2 and a 2. And I do those the way we were just doing them right upstairs. Now, this plus minus plus would work if I went down a column or across the middle row, and no matter which way you do this, across any row or down any column, you will get the same answer. So it turns out there are 6 different ways to expand this determinant, but they all give me the same thing. So I might as well just use the one across the top row, which is this one. With this setup, look at this formula. A2B3, A3B2. If I had A in this row, that would be A2B3, E times I. A3B2, BF times H. That's this submatrix. This is here if A is in the second row and B is in the third row. This one, A1B3, A1B3, A3B1, they're in the wrong order. That's where the minus sign comes into play. It'll switch the order. Same thing here. So this works, and then my formula now becomes what goes on the top row there? What goes on the top row is something that tells me that this should be the first component, and this should be the second component, and this should be the third component, and those are the vectors I, J, and K. This determinant formula compacts this, and I am far less likely to make a sign error when I write this down because there's no signs in it. Here, I've got to remember what order to do all the subtraction in. People, I have been doing this for 30 years. I still had to look at the paper to get it right. Write it down as a determinant. Flows out as to which one's down and which one's up. So, an example. Let's do 3, -1, 2, cross 2, 2, -1. So the first thing I do is write in my unit vectors in the top row. The first vector becomes the middle row, and the second vector becomes the bottom row. As I go across the top row, I get I times the minor, minus J times the minor, plus K times a minor. The single most common mistake at this point, got that minus in the middle of the J. Now, do the 2 by 2s. Down, minus, up. -1 times -1 is +1, minus 2 times 2 is 4. -1 times 3 is -3. 2 times 2 is 4. 3 times 2 is 6, minus -2 becomes a +2. And so I get minus 3i plus 7j, because it's minus negative 7, plus 8k. If you'd rather, you could write that without the i's, the j's, and the k's in our angle bracket notation as components. Either one of those answers is correct. But you'll notice I didn't have to memorize which numbers go where. They were all right there in the original order in the array in our matrix. Pull out. I will freely admit, the first time I saw this, I'm like, oh, this is just, I don't have to memorize that ugly ass one. If you would rather memorize the formula, go for it. I'm not going to hold it against you. I think this is faster. Questions? Yes, sir.
So you're using, like, two vectors using x. How does this differ from like the?
Because the dot product gave me a number, right? The dot product says, take these two numbers, let's say 3, -1, 2, dot 2, 2, -1 is 3 times 2 plus -1 times 2 plus 2 times -1. That's a number, right? So it just multiplies component by component and adds.
The dot product is more like just the magnitude, as this is like a whole new factor.
Well, remember that our dot product gave us something to do with angles, right? And you're right, this is a whole new vector. So that's my next question is what does this look like? What is this vector? Where is it? That's a good question, isn't it? Would it be between them? Would it be, oh, wait a minute, remember we're in 3 dimensions, right? So if I have 2 vectors, I don't have to lie on the same plane. I could stick out in some weird direction, right? So let's think about the angles, because Hayden was right that the dot product gives me something different. It gives me something about angles. So let's look at the angle between these 2 vectors. We do the angle, the cosine of the angle is a dot b over length of a, length of b. So let's just do the dot product to start with. That'll tell me if the arrow is less than 90, the angle is less than 90 degrees, bigger than 90 degrees, or at 90 degrees. What's that dot product? Aha. And if my dot product is 0, then what do I know about the angle? Exactly 90 degrees. What if I check the other one? That's also 0. -6 plus 14 minus 8 is again 0. What the? My original 2 vectors. 3, I could do this hand wavy position thing again. I'm not going to bother. I have 2 vectors to start with, A and B. I want something that's perpendicular to both of them. Do it this way. If these are my vectors A and B, what's something you know is at 90 degrees to each of them? Something coming straight out of the page at you. Right? So it turns out that this is true all the time, and that the vector A cross B is perpendicular to A, and the vector A cross B is perpendicular to B. So there is a new vector that we've just found, and it's in a different place, and it's sticking out at us. Well, if I had two vectors, A and B, no matter where they are, in the other box. No matter where those two vectors are, they form a plane. I don't care if they're like this, I can just fill in the surface between them, right? So here are my two vectors making a surface. And my cross product sticks out of that, perpendicular to it. No matter which way this is oriented, this has got to come out. There are two choices. It could come out this way, it could come out this way. Come out on top or on bottom. How do I know which? Unfortunately, here are my two vectors in a common plane. The vector that sticks out from both of them sticks out in the direction of my right hand from A to B. What the hell does that mean? Take your forefinger and point it in the direction of A so that the palm of your hand, or your middle finger, like when we do this, is pointed towards B. So you can think of it as curving towards B. Right? That's the direction I want to go. My thumb points the correct direction for the cross product. If I'm going from A to B, then my cross product sticks up. In this picture. Now that's a really crap picture, I freely admit, which is why I like saying that this is a right-handed idea. But even when I get to good pictures, like the one in the textbook here on page 816, you'll notice they've put it in exactly the same terms. We think of our direction the way our hand curves from A to B. This is the bottom of page 816. It's a right-handed idea because we're in a right-handed system. If I use my arms, A and B, then the cross product comes out the top of my head. Yes, sir. If it was B to A, I'd still use my right hand and it would go down. Wait a minute. Those are pointing in opposite directions, aren't they? A to B and B to A. Turns out that whenever I do that, I get exactly a minus sign. All the numbers stay the same. So if I did 2, 2, 1 cross 3, negative 1, 2, if I switch the order, I'd get positive 3, negative 7, negative 8. Numbers would be the same, the signs would be reversed. Again, a matrix reason for linear algebra that justifies that. You're switching the rows in the matrix you've drawn. That changes the IJK pluses and minuses. But it doesn't change anything else. That's an ugly looking picture. I apologize. Because to me, it's kind of hard to keep track of because it's flat. That's sticking up out of this embedded surface. That's why there's a right angle here and a right angle back there. This is where Tinker Toys come into play, right? I can put together a little model with balls of clay and toothpicks. A to B goes in the direction of my thumb. B to A goes in the direction of my thumb. Advantage, it doesn't have to be up or down. It could be forward or backwards or oblique at some angle. I just have to figure out where those two vectors are pointing and then set up my frame of reference. Glad I have this. It helps. But really what that tells me is that two vectors define a plane because they all come out of the origin together, right? So this is the point 0, 0, 0. And my two vectors are sticking in some directions. That's 3 points, and 3 points is exactly what I need to make a flat surface. Questions? Dr. Bijay?
Notation, you have the straight brackets around the cross, that's the find the length of it.
These are just parentheses. Length is absolute value. But that does give me a question then. What would absolute value give me here? Well, it turns out that there's a nice geometric interpretation here, like there was for the dot product. Dot product dealt with the cosine because we drew that little triangle, right? I'm going to draw something different. Let's draw like we were adding. Let's draw a copy of A and a copy of B. And remember, we have this angle theta that's going from A to B. Well, now I don't have the length of the side of the triangle. I have a parallelogram. It turns out the area of this parallelogram is length of A times length of B times the sine of theta rather than the cosine of theta. That's just a geometry formula that I've stolen right out of the geometry class because it's base times height, but this is not a right angle, so I need to insert a little right triangle here, make that a right angle, then that's height, and that's B hypotenuse times sine of theta. That's straight out of trig and out of geometry. I'm good with that. Turns out these are the same. Now, if I multiply by a -1, Jalen, that doesn't change the length of my vector. So the length of A cross B and the length of B cross A are the same. It's just the direction that changes. Where is sine of theta equal to 0? What angles? 0 and 180. If my vectors are at an angle of 0, they point in the same direction. If my vectors are at an angle of 180, they're on the same line, just in opposite directions, right? They're either parallel, anti-parallel. The dot product told me when things were perpendicular. Cross product tells me when things are parallel. If my cross product is 0, then my vectors lay on the same line. They're either parallel or anti-parallel. The textbook actually doesn't use the phrase anti-parallel, because lines are what are parallel or not, and those vectors then become lines, and I don't like that, because parallel to me orients a direction, and vectors have a direction to them. I use that phrase anti-parallel to mean 180 degrees. Whew. Questions? I now have 3 points, which I have defined in 3-dimensional space, which means I can draw a triangle. I need 3 pieces of information. I want the angles in this triangle. And I would like the area of this triangle. Now, this is again where I freely admit I am a visual thinker. I don't know where these 3 points are in 3 dimensions, but I do know any 3 points have a plane in common. So I might as well draw all 3 of these dots as if they're on the surface of this piece of paper. This drawing is absolutely not to scale. I have no idea if these sides or angles that I've drawn are even close to right. It doesn't matter. I've got a triangle. I want you to find 3 angles and an area. Which angle do you want to find first? The angle at P, the angle at Q, the angle at R. All right, if we're going to do the angle at P, how am I going to do that angle? I want to find an angle. Angles were what we used the dot product for, right? But I need 2 vectors to do a dot product. What 2 vectors do I use to find the angle at P? Exactly. To find the angle at P, I use PQ and PR. Which means I have to turn these points into vectors. It's head minus tail. PQ goes this way. Let me write the numbers with each one. So I have them right down here. What is the vector PQ? Exactly. It's the points at Q minus the points at P. So it would be perfect. And then PR would be the points at R minus the points at P. One minus one, negative one minus four, and one minus six. And now I know how to figure out the angle, yes? Cosine of angle P is PQ dot PR over length of PQ, length of PR. And because I have PQ and PR, I can do that. Right now, I'm not going to, but I can. How do I find the angle at Q? Aha. The important piece of that is I have to do QP and QR. I can't use PQ. PQ points this way. And if I did PQ and QR, I wouldn't be in my triangle, would I? I'd be on the outside of my triangle. So I need to be careful. To do an angle at Q, I use QP and QR. And I do the same calculation. How do I find the angle at R? I could, but there's a faster way. So we just, they add up to 180 degrees. If I have the two of them, I know the third one. So I only have to do 2 out of 3. I could do any 2 out of 3. I could do R by doing RP and RQ. That absolutely works. But at this point, having done P and having done Q, R I get for free. Maria, question?
I'm just sorry, how do you get it?
Oh, it is head minus tail. So it's -2 minus 1, 5 minus 4, and -1 minus 6.
Okay.
And then PR the same way. So I can get all 3 angles. Check. Now for the other part of this question. How do I find the area of this triangle? There are several different ways. Lots of them are just geometry ways. I'd like a vector way. What I say to myself is, no, I'm not going to find the area of a triangle. I'm going to cheat. I'm going to find the area of a parallelogram. We already wrote out PQ and PR, right? There's a copy of PQ. And here's a copy. I'm sorry, this is a copy of PR over there. This is a copy of PQ down here. Right? Like we were adding, we go head to tail. That's a parallelogram. Question for you. How does the area of the parallelogram relate to the area of the triangle? Because this triangle is an exact copy of that triangle, isn't it? How do I find the area of a parallelogram? Oh, that's our cross product. So the area of my triangle is half the length of the cross product. By the way, you could use PQ and PR. You could use QP and QR. You could use RP and RQ. I don't care which pair you use. It works out the same either way. You sneaky booger. So there are several different ways to picture what's going on here in three-dimensional space. But our cross product, given that it sticks out and given it's related to the sine of those two angles, as they get closer and closer, this gets smaller and smaller and smaller. When they're parallel, it's zero. We fell into nothingness. If you think about it, the area is getting smaller and smaller and smaller until it becomes zero. So this cross product goes to zero. Whew. Questions? Oh, sure. PQ cross PR. IJK. PQ is -3, 1, -7. PR is 0, -5, -5. I do my cross product. I times 1, -7, -5, -5, minus J times -3, -7, 0, -5, plus K times -3, 1, 0, -5. So that's I times -5 minus +35 minus J times -15 minus 0 plus K times +15 minus 0. So I get as my cross product itself -40 plus J times 15 plus K times 15. I'll write it as -40, 15, 15. And now I need the length of that, right? Well, this number is going to suck because to do the length, I have to do the square root of each of those squared. Uh, 40 squared is 1600. 15 squared is 225 twice. So that's 1600 and 450. That's the square root of 2050. And then I divide that by 2 to get the area of the triangle. Square root of 2050 is a disgusting looking number. Half of that is the area of my triangle. I would point out to you that I, in my notes here, did QP cross QR and got 40, 15, -15 because it points in a different direction, right? 40 and 15 are still my numbers. It's still the same length. The area doesn't change regardless of which corner I work at. Go ahead.
So whenever we're finding the angles of like Q and R,
Yes.
and then we find the area of the triangle where Q already basically exactly works.
All we have to do is the cross product. Yeah. Yep. So the area of the triangle equals 1/2 square root 2050. More questions? Okay. There are a bunch of properties for the cross product that carry through the algebra we like. But this first one is the one that's different. When you reverse the order, you get that minus sign in there. If I have a number, I can pull it out in front or I can put it on the other one. Distributive rules work on both sides because order matters. I have never used a triple cross product ever in my entire life. I don't know why they gave me this formula. I've literally never used it. The one above it, on the other hand, that's the one I think is interesting. A dot B cross C is A cross B dot C. If I rearrange the parentheses, I have to switch the multiplications. What the? So I'm perfectly willing to ignore number 6. But number 5, I need to think about for a minute. They had parentheses around the B and the C, right? I claim those parentheses are not needed. Think about the way you would multiply. If you multiplied from left to right, you would do A dot B first. What is the result when you do A dot B? It's a number. You go to do number times something, you can't do that. Because when you do a cross product, it's got to be a vector and a vector. So if I do this first, that's a number, and this broke right there. There is a pair of lame jokes that go with this. What do you get when you cross an elephant and a grape? Elephant, grape, sine theta, of course. What do you get when you cross a mosquito and a mountain climber? You can't do that. You can't cross a vector with a scalar. A mosquito is a disease vector. It transmits disease. The person who climbs mountains scales them. I heard those jokes 35 years ago. They've been with me ever since. That's why I know I can't do this. You can't cross a scalar with a vector. So these parentheses are automatic because that's the only way this product makes sense. Okay, wait a second. Let me see if I get this. This is going to do that, right? That's our B cross C setup in a matrix. Now, if I do that, and then I do A1, A2, A3, let me go way back to the formula setup back here. This would be an I, this would be a J, this would be a K, right? If I do a cross product like this, I, J, K. When I do a dot product, the dot product tells me take the I term times the I term. Take the J term times the J term. And the K term times the K term. So that would take A1 times that little piece. And A2 times the piece we get from those. And A3 times the piece we get from those, right? Wait a minute. A1 times the piece we get from those. And A2 times the piece we get from those. And A3 times the piece we get from those. Couldn't I just do that by replacing the IJK with A1, A2, and A3? Holy moly, there's an easy way to write this formula as well. It's a determinant. That is a number. That number is called the scalar triple product. Ready for the best part? That's got a geometric interpretation too. Bottom of page 819. This picture is of a three-dimensional version of a parallelogram. It's called a parallelepiped. Parallelepiped. But you can think of it as a box that got tired. It's kind of leaning over a little. The bottom's not square. The sides aren't square. It's just kind of parallelograms on all the sides. The area of the bottom is the cross product, B cross C. The height, look at this angle. The height is on the adjacent side of a right triangle. That's cosine theta. That's A cosine theta. That's A dot B cross C. Now, change the letters and do A, B, C. And you would do A cross B dot C. And that's where Formula 5 comes from. Because the volume of this object is this. This expression is the volume of the parallelepiped with sides A, B, and C. If this volume is 0, then your three vectors lie in the same plane. Instead of sticking out, the roof is collapsed. Instead of having a box, we have a flat object. Screwdrivers. Not vodka and orange juice, the tool. Screwdrivers. How does a screwdriver work? Which way? Why? Righty, tighty. It's a cross product. My direction of motion from A to B, in. From B to A, out. It's a right-handed system. It's a cross product. And what you're doing is you're applying force with a twist, right? There's a name for that. What's force with a twist? Torque. If you are applying a torque a distance away, you are applying a force at an angle, you take the cross product, R cross F. Torque is a cross product. So if you have a nut or a bolt that is stuck, you have two choices. Use more force or use a longer handle. Every motor assistance vehicle on the face of the planet has a 6-foot hollow pipe. So that when they go to take the lug nuts off your tire, if they're stuck, they can put that over the end of the wrench and push with a longer handle, increasing their torque by increasing the radius rather than trying to push harder. Useless crap. I'm never going to need it anywhere. Every freaking flat tire I've ever had. Tomorrow, no, not tomorrow, Wednesday. Wednesday is question and answer day. 12-1, 2, 3, and 4, all of which will be due Thursday. So if you've got questions, bring them on Wednesday. I will see you all then. Have a wonderful rest of your day.